This is the screencast for section 7.2, example 4. Now what if we have boundaries that change around the area of a curve? So example 4 here, it says find the area of the region R in the first quadrant, okay, that is bounded above by y equals square root x, that's this one here, and then below by the x-axis and the line x minus 2. So our top minus bottom, the bottom's going to change. The bottom over in this region here is y equals 0, but the bottom over here is y equals x minus 2. So our strategy is going to be to take the area of region A and add it to the area of region B to get our total area. So let's look at region A first. Region A is bounded above by y equals square root x and below by y equals 0. So that is the antiderivative then from 0 to 2. 2 is where that boundary ends, y equals 0 ends, and the other one picks up. So from 0 to 2 of square root x, technically minus 0, but I left out the minus 0. Take the antiderivative, fundamental theorem part 2, and I get that the area of region A is 4/3 times the square root of 2. So now let's look at region B. B is bounded above by its square root x, but below by x minus 2. So I'm going to take the antiderivative from, this time starting at 2 out to 4, so those x values, of the top, so square root x minus the bottom, x minus 2, dx of course, and then integrate, fundamental theorem part 2, and now if I take both of these and get my total area, it's going to be 4/3 square root 2 plus this whole mess that I started to simplify from region B, and then more and more simplification, and I get the area is 10/3. In your calculator, if you wanted to check this, you would have to do this in 2 parts. You'd have to find the area in region A and then add it to the area in region B. Then now try problem number 9. It says find the area of the shaded region analytically. So we're going to do this one by hand, and if I look, I can kind of see there's 3 curves creating the boundary of this shaded region. So if I look more closely, I can see that the top curve is going to change this time. So between 0 and 1, the top curve is y equals x and the bottom is x squared over 4. But then, as I continue on drawing little vertical lines to kind of mimic my rectangles, the top of the rectangles on this right side would be y equals 1, and the bottom will still be x squared over 4. So I have to find the area of these 2 different regions and add them together. So the first region is going to stretch from 0 to 1 on the x-axis, and that's going to be the antiderivative from 0 to 1 of x, the upper curve, minus x squared over 4, the lower curve, dx. Then I need to add the part that stretches between 1 and 2 on the x-axis. That upper curve, that boundary, the top one, is going to be 1, y equals 1, and the lower boundary is going to be x squared minus 4. So now I can integrate each of those, do fundamental theorem part 2, plug in 0, that wipes that out, simplify a whole bunch, and I get a final area of 5/6. And you might be thinking, wait a second, a little bit over 1? But look at this. If I made a big rectangle out of a 2 by 1, that's a unit of 2. And it does kind of look like that's shading a little more than a half, so a little over 1 unit in that rectangle of 2 units.